Welcome to the deep dive. Today, we're focusing on something so simple, so basic, you probably do it without thinking washing your hands.
Right. It's just automatic for most of us now.
Exactly. A cornerstone of public health, really. But getting here, that took, well, centuries. It was a whole intellectual revolution.
Oh, absolutely. And you use that phrase, intellectual revolution. We really need to stress that because the starting point, say the early 19th century, it was frankly shocking.
Oh, so.
Hospitals back then, they weren't places of healing, not always. They were often called houses of death. And get this,
Yeah.
physicians, the top guys, they'd go straight from dissecting a corpse,
Wait, seriously? From an autopsy?
straight to the maternity ward to deliver a baby. No hand washing in between. They were completely unwitting vectors of disease, deadly vectors.
Yeah. I mean, you can sort of picture the mindset, maybe, the arrogance, to even suggest these esteemed gentlemen were the problem.
Oh, it was unthinkable. More than just an outrage, suggesting they were spreading death. That was basically a career-ending move.
Because the established medical thinking just couldn't handle it.
Couldn't process it at all. The idea that something invisible, carried on their hands, was causing these terrible infections.
Yeah.
It flew in the face of everything they believed.
So our mission in this deep dive is to track that whole story. From, ancient instincts about cleanliness through the tragedy of the man who first proved it with data.
Ignaz Semmelweis, yeah.
Yeah.
A tragic figure.
Then the scientists who finally explained why it worked, the germ theory guys. And finally, the kind of surprising chemistry and industry that made soap, the tool itself, available to everyone.
It's quite a journey, from instinct to chemistry.
So let's dive in. Where do we start? Before the 19th century drama.
Yeah, let's go way back. Because the drive for cleanliness itself, it's incredibly old. It's not just human. You see it all over nature.
Like animals.
Exactly. Think about ants grooming themselves constantly. They're removing fungal spores. Or sheep. They naturally avoid grazing near where other sheep have left droppings. Reindeer migrate away from contaminated grounds. It's ancient adaptive behavior. Evolutionary.
So it's wired into us, basically, a survival thing.
Pretty much. And in humans, one way this seems to manifest is through the emotion of disgust.
Ah, right. That feeling you get from spoiled food or waste.
That's the theory. Disgust likely evolved as this sort of built-in disease avoidance system. It's pretty rational. Hygiene first, understanding later.
Okay, so we have this basic instinct, but how did it become, a societal practice?
Well, often religion stepped in. It provided this really powerful sort of scaffolding for public health long before anyone knew about germs.
You see hints in early texts, right? Like the Egyptian Ebers Papyrus around 1500 BCE.
Yeah, and Hippocrates mentioned hygiene, but the big religions really codified it. Judaism has Netilat Yadayim, the ritual hand washing. Islam requires wudu, ablution before prayer. There's that famous saying, cleanliness is half of faith.
So these practices embedded hygiene into daily life for millions based on, tradition and maybe that underlying instinct.
Exactly. But then, fast forward to the dawn of modern medicine in the West, and these useful traditions were kind of sidelined by two dominant and ultimately wrong theories.
Okay, what were they?
First, you had the humoral theory, the ancient Greek idea that disease came from an internal imbalance, blood, phlegm, black bile, yellow bile.
Right, the four humors.
So if sickness is an inside job, the idea of catching something specific from outside, from someone else's hands, it just doesn't fit the model. It's counterintuitive.
Okay, that's one. What was the other big one?
Miasma theory. This was huge in the 19th century. The belief that disease was caused by bad air, a noxious vapor, a miasma rising from rotting stuff, sewage, garbage, corpses, swamps, even just dirt.
So if it smelled bad, it was bad. The smell itself was the danger.
Precisely. The sensory link was everything. There's this prominent sanitarian, Edwin Chadwick, who declared in 1846 something like, all smell is, if intense, immediate acute disease. The smell was the disease agent, not just a sign of it.
But here's the really fascinating part, isn't it? Miasma theory was completely wrong about the cause.
Totally wrong. It's not vapors.
But it actually led to positive actions, right? Because people were so focused on getting rid of bad smells.
They started massive cleanup projects, improving drainage, venting sewers, removing garbage, cleaning streets and homes, all to fight the smell.
And by doing that, they accidentally got rid of the actual breeding grounds for bacteria and other pathogens.
It's this incredible historical irony. They cleaned up the environment for the wrong reason, but it worked anyway. Florence Nightingale is the prime example.
The lady with the lamp in the Crimean War.
She was a staunch miasmatist. absolutely convinced bad air was the killer in those horrific field hospitals. So she focused relentlessly on ventilation, fresh air, removing waste, scrubbing floors.
And crucially, she also insisted on cleanliness, clean bedding, clean bandages.
And hand washing for her nurses. Even though her theory was off, her practices were spot on. She dramatically cut mortality rates, achieved the right outcome just based on the wrong scientific framework.
Which sets the stage perfectly for Dr. Ignaz Semmelweis in Vienna. He's the one who really collided with the established dogma using data.
Yes, 1846, Vienna General Hospital. He's working there and gets confronted by this horrifying pattern with puerperal fever, what they call childbed fever.
This was in the maternity wards.
2 of them. The first clinic was for training doctors and medical students. Its maternal death rate was shocking, averaged around 10%, but sometimes shot up to nearly 30%.
1 in 3 mothers dying. That's terrifying. Expectant mothers must have been desperate to avoid that clinic.
They were. They literally begged not to be sent there, because right across the hall was the second clinic.
Staffed by midwives.
Only midwives. And their death rate, consistently under 4%,
Right.
often lower.
Okay, so same hospital, same time, vastly different outcomes. Something was clearly different about that first clinic.
Semmelweis was obsessed with figuring it out. He tested everything. Birthing positions, ventilation differences. He even considered if the priest walking by to give last rites was somehow scaring women to death.
Seriously, he looked at that.
He looked at everything. The breakthrough came in 1847, but it was tragic. His friend and colleague, a pathologist named Jacob Kolechka,
What happened?
he died after accidentally getting cut by a student's scalpel during an autopsy. And when they performed an autopsy on Kolechka himself.
Let me guess. The findings looked exactly like the mothers who died from childbed fever.
Bingo. The exact same internal inflammation and infection. Semmelweis had his light bulb moment.
The connection was the autopsies.
Yes. The doctors and students of the first clinic routinely performed autopsies in the morgue and then went straight to the maternity ward to examine patients, often doing internal exams.
Without washing their hands properly.
Right. They were carrying something from the corpses. The midwives in the second clinic, they didn't do autopsies. They weren't handling cadavers.
So Semmelweis formed his hypothesis. What did he call it?
He called the contaminants cadaverous particles,
Right.
invisible bits from the dead bodies transferred on the hands.
Okay, so what did he do? What was the intervention?
Simple, direct action. In 1847, he mandated that everyone entering the first clinic, doctors, students, staff, had to wash their hands thoroughly in a basin of chlorinated lime solution.
Chlorinated lime. Why that specifically?
Because it worked on the smell. Remember miasma? Smell was still linked to disease in people's minds. Chlorinated lime is a powerful disinfectant, but crucially for Semmelweis, it completely destroyed the foul, putrid odor that clung to hands after leaving the morgue.
So the smell removal was his proof, his sensory confirmation that the particles were gone.
Kind of, yeah. It fit the existing sensory clues while also having the right effect. And the results.
Tell me.
Absolutely staggering. Before the hand-washing rule, the death rate in his clinic had peaked at something like 18.3% in April 1847. After mandatory hand-washing, it plummeted. By 1848, the rate was down to 1.2%.
From over 18% to just over 1%, that's undeniable proof.
You would absolutely think so. Crystal clear data. Saved lives right before their eyes.
And yet, the medical establishment didn't rush to celebrate him, did they?
Celebrate him. They attacked him viciously. They rejected his findings, ridiculed him, and eventually forced him out.
Why? How could they ignore that kind of success? It makes no sense.
It makes a certain kind of terrible sense when you understand the context. This rejection is now famously called the Semmelweis reflex, the knee-jerk rejection of new evidence because it contradicts established norms or beliefs.
So what were the specific reasons they fought him so hard?
Well, first, it was a massive blow to their ego. The implication that they, respected gentlemen physicians, were personally responsible for killing their patients. Unacceptable. A profound insult.
All right. Okay. Or what else?
Second, his explanation fell too. Simple. Medical thinking at the time favored complex, multi-causal explanations for diseases like fever. They thought there could be like 30 different causes. One simple fix like hand washing seemed naive.
And the third reason, the big one.
He couldn't explain the why in terms they could accept. He had the what, wash your hands, people stop dying. But his cadaverous particles were invisible, hypothetical. He didn't have the underlying scientific theory to back it up. There was no germ theory yet.
So without the science, it just sounded like a strange personal theory, despite the results.
Exactly. It lacked the scientific weight. And the outcome for Semmelweis himself was just tragic. He was driven out of Vienna, struggled professionally. His mental health deteriorated under the strain and ridicule.
And didn't he end up in an asylum?
Yes. And the terrible irony is that he died there in 1865 from sepsis, an infection, likely from a wound, the very kind of infection he had fought so hard to prevent in others.
Unbelievable. So Semmelweis had the practical answer, but the world needed the scientific explanation. That came next, right?
Yes, the theoretical framework he lacked was built soon after, primarily by two giants, Louis Pasteur and Robert Koch.
Pasteur first. What was his key contribution?
Pasteur basically demolished the centuries-old idea of spontaneous generation. The belief that life, like microbes, could just arise spontaneously from non-living matter, like broth or decaying flesh.
How did he disprove that? I think I remember this from school. The flasks.
The famous swan-necked flask experiment. He showed that if you boiled broth in a flask, sterilize it, but used a long, curved neck that allowed air in but trapped dust particles.
The broth stayed clear. No microbes grew.
Right. But if you broke the neck off or tilted the flask so the broth touched the trapped dust, then microbes appeared. It proved the microbes came from the air, from existing microbial life, not from nowhere.
That feels like a fundamental shift in thinking. Things don't just happen, they have a cause, an external cause.
Precisely. It opened the door to understanding that these invisible microbes were real entities, capable of transfer and causing change. Pasteur then went on to show they caused fermentation, which led to pasteurization.
And importantly, disease. He linked specific microbes to diseases in silkworms than animals.
Setting the stage for the germ theory of disease. But Pasteur provided the big picture, the theoretical possibility. It was Robert Koch who provided the rigorous method.
Okay, so what did Koch bring to the table?
Koch turned bacteriology into a proper experimental science. He was incredibly methodical. His huge breakthrough was figuring out how to grow bacteria in pure cultures.
Meaning isolating just one type of bacterium at a time.
Exactly. He developed techniques using solid media, like agar plates, so he could grow distinct colonies, each starting from a single bacterial cell. Before Koch, scientists were mostly looking at mixed microbes and liquids, which made it impossible to prove which one caused what.
And this led to his famous postulates.
Yes, Koch's postulates. A set of 4 strict criteria that had to be met to prove, beyond doubt, that a specific microbe causes a specific disease.
Can you quickly remind us what they are?
Sure, basically. 1, find the microbe in all cases of the disease, but not in healthy individuals. 2, isolate the microbe and grow it in a pure culture. 3, introduce that cultured microbe into a healthy host, and it must cause the same disease. 4, isolate the same microbe from the newly infected host.
Wow, that's rigorous. Left no room for doubt.
He used this method to nail down the specific bacteria causing major diseases like anthrax, tuberculosis, and cholera. Game-changing work.
So Pasteur's vision germs exist and cause disease, plus Koch's method, here's how you prove which germ causes which disease.
Together, they provided the rock-solid scientific foundation that Semmelweis was missing. His cadaverous particles could finally be understood for what they were: pathogenic bacteria.
The scientific loop was closed. But there's another piece to this puzzle, isn't there? Knowing about germs and washing hands is one thing, but you need the tool. You need soap.
Absolutely. And soap has its own fascinating parallel history. For hand washing to become a truly universal public health measure, soap had to stop being a luxury item.
It wasn't always used for personal hygiene.
Not at all initially. The earliest evidence, maybe around 2800 BCE in Babylon, suggests soap was used more for industrial purposes, like cleaning wool or textiles.
What about the Romans, famous for their baths?
They used oils and scraped their skin clean with the tool called a strigil. Soap existed, but they seemed to regard it more like a hair pomade, something the Gauls used. Definitely not for lathering up the body.
So when did it become more refined?
Things improved in the Middle Ages, with products like Castile soap from Spain made with olive oil. But it was still relatively expensive, a high-end item for the wealthy.
What kept it so expensive for so long? Was it just hard to make?
Production methods were part of it, but a huge factor, especially in places like Britain, was politics and economics.
Taxes.
They taxed soap. Oh, yeah. Britain had a heavy soap tax that lasted for an incredible 141 years. It was taxed by weight during production, making it prohibitively expensive for ordinary working families.
So even if people understood cleanliness was good, they literally couldn't afford the soap to do it properly.
That was a major barrier. The game changed thanks to the Industrial Revolution and a key chemical breakthrough. In 1791, a Frenchman named Nicolas Leblanc patented a process to make soda ash, sodium carbonate, a vital ingredient for soap, cheaply from common salt.
Making one of the key ingredients much cheaper.
Exactly. And when that industrial process combined with the eventual repeal of that crippling English soap tax in 1853,
Suddenly, mass production became possible and the price dropped.
right, that combination, cheaper production and no tax, alongside the growing acceptance of germ theory, finally allowed soap to shift from being a luxury to being a common, accessible household necessity.
Okay, so now we have the science, germs, and the tool, affordable soap. Let's get into the really cool part. How does soap actually work at the molecular level? It's more than just making things slippery, right?
Oh, much more.
Yeah.
It's actually a brilliant piece of microengineering. Soap molecules are fascinating things called surfactants. Think of them like little pins. They have a head that loves water, hydrophilic,
Mm.
and a tail that hates water but loves oils and fats, hydrophobic.
Okay, head loves water, tail hates water. How does that fight germs?
So the dual nature is the key. Let's talk mechanism one, destruction. Many viruses, like influenza and coronaviruses, and many bacteria have an outer envelope made of lipids, basically, a fatty membrane.
Okay.
Those hydrophobic, water-hating tails of the soap molecules, they see that fatty membrane and they want in. They aggressively wedge themselves into the pathogen's outer layer.
Like tiny little crowbars.
Exactly like molecular crowbars. They pry apart the lipid membrane, rupturing the virus or bacterium. The contents spill out, and the pathogen is destroyed or inactivated. Gone.
Wow, that's pretty aggressive. So that's mechanism one, brute force destruction. What's mechanism two?
Mechanism two is about removal, and it's crucial for all sorts of grime, including pathogens that don't have that fatty outer layer, like norovirus, which can be really tough.
Right, some germs are harder to kill.
So when you lather up and scrub, the physical action helps lift dirt and microbes off your skin. Then those soap molecules do something else clever. Their hydrophobic tails grab onto the bits of dirt, grease, and any remaining pathogens, dead or alive.
And the water-living heads.
They point outwards towards the water. They form these tiny spherical cages called micelles, with the dirt and germs trapped inside, surrounded by the soap molecules.
Like little soap prisons for the germs.
A perfect analogy. And because the outside of the micelle cage is the water-loving heads, when you rinse your hands under running water.
The water just washes the whole cage away, taking the trapped gunk and germs down the drain.
Precisely. So it's a combination. Destroying vulnerable pathogens directly, and then lifting and trapping everything else, dirt, grease, microbes inside micelles, to be rinsed away. Powerful stuff.
Which explains why the way you wash is so important. It's not just a quick rinse.
Absolutely not. That's why the WHO and CDC have standardized guidelines, those 5 essential steps. Wet, lather, scrub, rinse, dry. They all matter.
And the scrubbing part, the duration, is key, isn't it?
Critically important. You need to scrub all surfaces of your hands, backs, between fingers, under nails for at least 20 seconds.
The time it takes to sing happy birthday twice.
That's the famous mnemonic, yeah. That 20 seconds gives the soap molecules enough time to do their work, both the crowbar action and forming those micelles. And the friction helps physically dislodge things.
And we should wash often, right? Before eating, after the toilet, after coughing or sneezing.
All those key moments. And just to clarify the sanitizer question, alcohol-based hand sanitizer, at least 60% alcohol, is a good alternative when you can't use soap and water. It kills many germs.
But soap and water is the gold standard.
Always preferred, especially if your hands are visibly dirty or greasy because the soap lifts that away. And soap is better against certain tough bugs like norovirus or C. diff. Sanitizer doesn't work as well on those.
So recapping the whole journey, we started with instinct, moved through flawed theories like miasma that accidentally helped,
Then hit the tragedy of Semmelweis, who had the proof but no accepted theory.
followed by the scientific revolution of Pasteur and Koch, finally explaining the why.
And paralleled by the Industrial Revolution making soap cheap enough for everyone. It took all those pieces falling into place.
It really is an amazing convergence of observation, science, and industry. And yet, here we are, we know all this, especially after the intense focus during the COVID-19 pandemic.
Right. You'd think hand-washing compliance would be near 100% now.
But it's not, is it? Even in hospitals, studies show compliance isn't perfect. People know they should, but they don't always do it.
Which means the cutting edge of this story is shifting again. It's moving beyond epidemiology and microbiology.
Into behavioral science, psychology.
Exactly. The big challenge now isn't really understanding how soap and water works. We've got that down. The challenge is understanding human behavior well enough to make this simple, ancient, life-saving action a truly universal, unbreakable habit.
So the final frontier is us, our habits.
Pretty much. Which leads to maybe a final thought for you, our listeners, to chew on. We had Semmelweis's tragic proof. We had the global pandemic push in 2020. What's it going to take next? What kind of event, or perhaps what kind of behavioral insight, will finally close that gap between knowing we should wash our hands and actually doing it every single time? What will finally make it stick permanently?